Like different a figure or something. How's it going? You did the homework. Oh,
So what? Did the lab work? Get it working? Controlling? Little tune of the function generator knob, and your controller will adjust the frequency back. Very little tune. Somebody, yes, Jonathan. You can ask questions on the homework, yes. We'll see if I answer them.
Okay, well, because like I was reading it, it says show how to implement those macros, and then I went to the section, and isn't the code already there for the macro? Like, I don't have my book with me, but like, it gives you some code and says this is how you could implement this and see, and it says here are some macros.
Okay, so like with the slides that I showed, so the question is, does the book already actually implement those macros? I mean, what should we do? So the book has something similar to what I showed in slides. You go to exam 2 solutions real quick. Yeah, there we go. Okay, so this right here is what your C program that you write using the macros should look like. So this is instantiation of the macros. Okay? What are the definitions of the macros? Well, the definitions of the macros would be like this. You're going to fill in what the various implementations of those macros are. What should that expand out to? It should expand out to something like this. Okay? So the whole idea is to get out your Japanese cleaver, chop up this file, and put it into those macros. Okay? But it's never okay to turn your brain off. Okay? So the whole idea is you don't just take this literal file and chop it up and put it into macro definitions. You got to make it work for, if I want to declare whatever exception I want to, a new exception, and if I want to declare 15 exceptions and use them all, I should be able to do it. Okay? So you just have to have an approach where you take these guys, divide them up appropriately, and instantiate or provide your macro definitions, and then compile a few different macro instantiations and make sure that it actually compiles and runs with your C compiler. Okay? So we get you a lot of the way there, saying kind of this is what it kind of is supposed to expand to, and we show you how to use the macros, but we don't give the macro definitions. So you still got to figure out what goes where in the macro definition. So this problem is due tomorrow. I hope nobody feels like I just busted that one on them real soon, because you've known about this one for a while. Don't give me that. Don't give me any of that I just busted on you real quick. Questions about the macros? All right. Okay. Save area is a jump buff. It's a type jump buff that's in the type of it defined in the header file that gives you the prototype for set jump and long jump. Was that your question? Okay.
Does it have to be able to handle any number of exceptions that you want to define, or is there a finite number that you...
Okay, so it has to be able to, so the question is there a finite upper bound on the number of exceptions that we can handle? The rule that I will give you is I have to declare an exception before I use it, but I'm not telling you I have a cap on the number of exceptions I can declare.
Okay.
No statically defined arrays. I'm so darn close with these midterms. Ugh. Not quite there yet. The average right now, I'm about, I've graded all of problem 1 and all of problem 2. A lot of times grading problem 1 was really easy. Yeah, but that means it was a lot of blank. A lot of, oh boy, we need to sit down and talk. But I'm just in the middle. I've got about half of the problem 3s done, and I'm totaling the exams as I go. So I've got about half of the class done, and just so you know, the average right now is running at about a 60. The standard deviation is running at about a 22 or so. That's really big. I've got a 95. I've got a 22. I don't know what to do with this. Where's your gun so you can shoot them? All right, so Levi will take the fault for that one. Okay, so today we get to continue talking about context switching. This stuff is arguably the most confusing lecture I'm going to give today. I'm going to give this semester. You got to pay attention, and I'm sorry in advance. Okay, it's really cool stuff, and it took a whole lot of pounding and beating on this stuff between me and Rohit to develop this code to get the context switching working correctly. So I told you last time about context switch, and I told you how we can save state on the stack. All processes get their own stack. We push the state of the processor, and we move on from there. We switch stack pointers. So just as long as in context switch, we push all the registers, and then we keep track of where the top of the stack was after we pushed all the registers. All we have to do is just point the stack pointer at a different context, unload all the saved registers from that context, and go back to what we were doing before. That's effectively the gist of a context switch. The problem that we have is this little issue of having an interrupt stack. So we have different modes of our processor. So we titled this lecture, "The Truth, the Whole Truth, and Nothing But the Truth." The context switch that I gave you last time doesn't work. It'll work if we're doing cooperative context switching only. But if we're trying to do preemptive context switching, and preemptive context switching is where you have an interrupt, and you interrupt the program as it runs, and you context switch from the interrupted program. So we want to be able to preempt the process as it's running. So this process is running, I fire in an interrupt, and then I call context switch from the interrupt service routine. And that causes me to freeze this program, this process that's running, and then I swap in a different process. Okay? That context switch code that we had could possibly be made to work if you're doing a preemptive if you're only supporting preemptive context switching. However, we want to be able to support cooperative context switching and preemptive context switching with the same CS code. So what that means is we want to be able to have a process that we swap out cooperatively. We want to be able to swap it in as if it were swapped out from an interrupt service routine. Okay? So this mixing and matching of this process was swapped out cooperatively, we're in the middle of an interrupt service routine and we want to swap it in. We've got a problem here because when we're in the middle of an interrupt service routine, what is the stack pointer register pointing to? Not the value that it's pointing to. What stack is it pointing to? It's pointing to the IRQ mode stack point, or the IRQ mode stack. Okay? The IRQ, we have a stack pointer register in IRQ mode. We have a stack pointer register in SVC mode. Every process gets their own stack. And as a process runs, we point the SVC mode stack pointer register to that process's stack. So under normal circumstances, when we're running and we get an interrupt, we go through the ISRs file, and we start to handle the interrupt, we get inside PIT. Aside from context switching, what happens is when we're inside PIT and we allocate a local variable, that local variable gets allocated to the stack. What stack? The IRQ mode stack. If you're going to knock, don't knock timidly. This is the thing that whenever people come to see me in my office and they don't know if I'm in there or not, they just come up to the door and I can't even tell if it's a fly or if it's a person knocking on the door. If you're going to knock on a door, knock on the door. Okay. So, anyway, we have in our interrupt service routine, if we declare a local variable or if we're going to save a call save register or something like that, and we push something onto the stack that gets used inside PIT is not the same stack that we're using when we're not in an interrupt service routine. Okay? So if you remember inside ISRs, what we did is we pushed all the registers onto the stack. What stack is that? The stack. Wait a minute, we don't have a the stack anymore. We have a the two stacks. Okay? So what stack are we talking about? It's whatever stack SP is pointing to. When we're inside ISRs, what stack is SP pointing to? It depends on the mode that the processor is in. The processor automatically puts us in IRQ mode by the time we start handling an interrupt. And that happens prior to our executing any line of code inside ISRs.s. So before we push any registers onto the stack, we're already in IRQ mode. So therefore, our stack pointer is not the stack pointer we started with. This is not our process's own stack. So now we have this problem of, let's suppose that I want to execute a context switch. I get interrupted. I push all my state onto the IRQ stack. Then I go in and I execute the context switch. I save all the registers again inside the context switch and push those onto the stack. And then I switch to a new process. That new process unwinds its context and pops all of its registers off of its stack, because we've got separate stacks for each process. And then it goes back to the ISRs file and pops from the IRQ stack all of the registers that were saved. But the problem is, since both processes are sharing the IRQ stack, the state that's saved on the IRQ stack is not the process's local registers. It's the other process's state. So we're sharing the state of two processes by virtue of the fact that the two processes share the IRQ stack, and because the ISRs file pushes the state onto the IRQ stack. So how do we keep the state separate for these two processes? Well, we could go through and have every process have its own IRQ stack, or we could go through and do the shenanigans that I'm going to tell you about today, and that's instead of having every process have its own SVC stack and its own IRQ stack, we're going to have every process just use the SVC stack to save its state whenever it saves state. So what that means is when we're inside an IRQ, we're going to have to switch the processor mode, and then push registers, and then switch back. And then switch processor mode, push all the registers, switch back. So we're going to push registers once in the ISRs file and once inside context switch. Why do we need to do it twice? Because we don't always, every time we get an interrupt, we don't necessarily always context switch. But we do whack registers. So like if you're handling the RPM interrupt, this interrupt has nothing to do with a context switch, so you want to make sure that your handling of an interrupt doesn't whack what your process is doing, so it's got to get an interrupt, push all of its registers, handle the interrupt, go back, pop all of its registers, and proceed. But sometimes you do context switch. So you've got to push all your registers because this is an interrupt, and then you go through and say, oh, I'm context switching, I need to push all my registers because you've changed some of the state of the processor as you've handled the interrupt. So when you're freezing this process, it's still got to unwind later on and go back through where it came to before it gets back to ISRs. Some of those registers have to be maintained properly in order for the interrupts to not get messed up. So we have to push the state twice. Do we have to push all of the state twice? Well, that's a question for Lab 6 that you get to address. So how do we go about doing this? How do we make sure that we can, inside an IRQ, save the state appropriately to the SVC stack instead of to the IRQ stack? The other problem is, whenever we context switch, we have to leave the IRQ stack in the state that it was in before we started the interrupt. Because if we swap this process out and another process gets swapped in, and let's suppose that process was swapped out cooperatively, and so it gets swapped in and starts executing its own business, if the IRQ stack isn't at its nominal state of where it was before we had any interrupt, when that process gets an interrupt, it'll push stuff onto the stack, pop stuff off of the stack. We could end up getting into a situation to where if we push stuff onto the stack and never pop it off, we push some more stuff and push some more stuff and push some more stuff, the IRQ stack could grow indefinitely. Okay? So we have to make sure of handling the two stacks correctly. So this leads to a big, nasty bunch of code. Okay. So a few things that you need to remember. IRQ mode, we use the IRQ stack pointer. If the processor is in SVC mode, we use the SVC stack pointer. What does the reference to the IRQ mode stack pointer or the SVC mode stack pointer look like in the assembly code? SP. Okay? They look just the same. Okay? So there's no way to tell by looking at an instruction that's doing a push which stack it's pushing to. You have to know what mode you're in. Okay? And this is where it gets kind of tricky. So you have to keep track of what mode am I currently in, and that dictates which stack pointer I'm pushing to. Okay. All processes share one IRQ stack. Each process has its own SVC stack. Okay, and we want to be able to support both preemptive and cooperative context switch with the same code. Okay. Another thing to remember, as I've told you last time, when you're pushing, you typically push to a stack pointer. You usually use an addressing register like the stack pointer register as your frame of reference for doing the push. So you say, I want to do an str, a store, and you pass it SP, comma, bracket, or you say the value, say R0. You want to store the contents of R0, comma, bracket, SP, comma, #4, close bracket, bang, or something like that. Some addressing mode, but you're referencing the stack relative to the stack pointer. ARM doesn't care if you use SP to do that. Okay? There's, like in x86, you have the push L instruction. That assumes you're using ESP. There's no hard wiring going on inside ARM to make you use SP for stack operations. So you can push and pop using any general purpose register as an address register. And specifically, we're going to use different registers in order to access a region of memory as if that were a stack. Okay? The stack pointer is R13. Which R13 we're accessing depends on which mode of the processor we're in. You can change the mode by writing to CPSR. You have to be in a privileged mode in order to write to CPSR. Okay? Preemptive context switching has to work in conjunction with the ISR's file. And we're going to make radical, massive, ugly changes to the ISR file. Okay? If you're in supervisor mode, it doesn't hurt to change to supervisor mode. So if I'm in one mode of the processor, I can change to the same mode and nothing breaks. Okay? And we're going to use that trick inside the context switch code to make the context switch code a little bit simpler. Anyway, here is our revised context switch, the truth, the whole truth, and nothing but the truth. This is the one that you're actually going to work on, and this is the one that works. Okay? It's very similar to what we were doing before, but we have a little bit of mode switching going on. Okay, so first what we do, STMFD, SP bang, so I'm pushing all the registers. This is just like what we had before. Okay? MRS, R2, CPSR. Again, remember that we have the destination register first and the source register second, so we're moving from CPSR into R2, then storing R2 onto the stack, decrementing the stack by 4. So we're pushing the contents of the CPSR. So now my question is, which stack pointer is this? Depends on whether or not we are in an interrupt or not. Do we know if we're in an interrupt or not? The whole point is this code should work regardless of whether we're in an interrupt or not. We want it to work if we call it straight from a process or if we call it implicitly from an ISR. So this code has to work either way. So we're not saying which SP this is because it could be either one. So if we call it from a yield function inside our code, then that means we're trying to cooperatively swap ourselves out. If we call it from PIT, that means we are preemptively swapping ourselves out. So the interrupt service routine is swapping this code out. So SP could be either the SVC SP or the IRQ SP, and it totally depends on what mode the processor is in when this starts.
What's a CPSR?
Current Program Status Register, CPSR. This register holds some bits that indicate what the mode of the processor is, and also the condition codes and a few other things. saves the current state. So registers contain state, CPSR contains state. So it is saving whatever, part of the context of a process is what's in that CPSR because it affects the behavior of the program, like what mode the processor is in and what the condition codes are. So it's one of the things we got to save, and this is how we save it. So push the CPSR, so we store all the registers, we push all the registers onto the stack, whichever stack it is whatever SP is pointing to. Then we push the CPSR, and then this is a little bit different than what I showed you last time. What we do is we take SP, we subtract 4 from it. We don't update SP with that value. We just take the value currently stored in SP, subtract 4 from it, and put that into R3. Okay? So then the next instruction says store R3 at SP minus 4 bang. So that says push R3 onto the stack. So I'm calculating first into R3 SP minus 4, then I'm pushing R3. Anybody see what that does? What should R3 contain? So can you tell me what, after this store instruction occurs, what's the value of R3 relative to the value of SP? This first instruction, the sub-instruction, subtracts 4 from SP. This second instruction subtracts 4 from SP and updates SP. Okay? So what I'm doing is I'm calculating in this sub-instruction, what will the stack pointer be after the next push? Okay? And then I'm pushing. So after I've done these two instructions, what I've got is R3 pointing to the top of the stack pointer pointing to the top of the stack, and the value stored at the top of the stack, being a copy of R3, pointing to the top of the stack. So I've just pushed a pointer to itself. I've pushed the top of the stack right here. So this is effectively the same thing as saying push the stack pointer on top of the stack, but decrement the stack pointer first before you push it. So calculate what the stack pointer is going to be after a push, then push that. So R3 points to the top of the stack pointer points to the top of the stack, and the value at the top of the stack is a pointer to itself. Which stack is this? Again, what mode are we in? This you will have to beat into your heads. What stack pointer is it? You have to be paying attention to which SP is this. It depends on the mode. Tony.
So we're looking at inside and interrupt.
We are not necessarily looking at inside and interrupt.
What I'm saying is, if we were inside an interrupt, it's going to be the interrupt that's going to be doing the context switching, right?
Right. So if we're inside an interrupt, then the interrupt gets to decide who he calls context switch on.
Right. So the interrupt sees SP. The SP it sees is pointing to its stack.
So if we're from an interrupt and we call CS, SP, we're assuming that with the processor is in IRQ mode, and so then SP is pointing to the IRQ mode stack.
Okay. But isn't it the stack of the other process that we want to switch out of that we need to
push all the registers onto? So now so this guy gets pushed on to the stack at whatever SP is pointing to. That SP is the IRQ mode SP.
Right.
But there's nothing saying that we have to point the IRQ mode stack pointer register at the memory that we've allocated as the IRQ mode stack.
Wow.
So the trick that we're going to show you is by the time we get here, from an interrupt service routine, we're going to point the IRQ mode stack pointer at the process's stack. That's what you call pulling the pants down on the context switch code. Okay. So we push all the registers, we push the CPSR, we push a pointer to the top of the stack onto the stack. Next. You remember R0 contains the first parameter passed to CS, which is the pointer to the memory location of where we want to store a pointer to the top of the stack that we're saving. So we're going to remember where we saved the old context. So we're storing SP, which is a pointer to the top of the stack. And if you remember, R3 is pointing here, SP is pointing here, and the top of the stack is also pointing at the same spot. So we just say I'm going to push SP onto this location here. So this is kind of like R0 is a stack pointer. Well, I take it back. We're just storing it at this pointer. We don't have a bang here. Okay. If we had a bang, it wouldn't make any difference because it's 0. Okay, R0. So we say store SP at the location pointed to by R0.
Destination second.
On store instructions, it's backwards. So we're reading from SP and storing here in the address. Yeah, that's kind of clunky. It just means that if you're addressing memory, the addressing mode has to come second in the instruction. ARM syntax, I didn't do it. Sorry. But that's the only one where source comes first. So store SP at the location pointed to by R0. So that just, what that does is it helps us to remember where is the context of the old process stored, and we store that in a separate memory location. Now we start to worry about loading the context of the new process. So to do that, what we do is we do this ORing operation. You remember R2 up here, we loaded with a CPSR. That is the current mode of the processor. Okay? None of these operations up here change the mode of the processor. This sub-instruction could change the condition code, but we have the mode of the processor here. We're going to change the mode of the processor with this OR operation. So this ORR is a bitwise OR. Okay? So we're ORing R2 with the value 0x1 and storing that into R3. And then the next instruction we're saying MSR CPSR underscore C, comma R3. This underscore C, what it does is it only writes some of the bits. So we identify the 4 bytes of the 32-bit CPSR with different letters, F, S, X, and C. Okay? The C bits are the lower 8 bits, and those bits are what control the mode of the processor. Okay? So this MSR is taking the lower 8 bits of R3 and moving it into the lower 8 bits of the CPSR. That will change the mode of the processor, or it could potentially change the mode of the processor. So what this is doing is I'm going to make sure that if we're not in supervisor mode, we're going to change the supervisor mode. If we are in supervisor mode, this doesn't do anything. It just changes us to the mode that we're already in. Okay, so this may or may not change the mode of the processor. But we do know that after 5, we're in supervisor mode. Yeah. The F, S, X, and C to represent the different fields. Yeah, there are. The C is for control bits. I can't remember what the F, S, and X stand for, but I think the X is executable. F is function. S, I can't remember. I'd have to. It's in the ARM reference manual that you got on the web. There is a reason. Mitch?
I thought you said that you can't change yourself to supervisor mode.
You can't change yourself from an unprivileged mode to a privileged mode. But we are already in a privileged mode. Supervisor mode and IRQ mode are both privileged mode. The only unprivileged mode is user mode, and we never touch user mode. So if you put yourself into user mode, you can't get out unless you call an interrupt.
So when our process calls yield, we're assuming that process was in supervisor mode?
All of our processes that we're dealing with in this class, we will never touch an unprivileged mode. We will always be in a privileged mode. You can deal with putting yourself into an unprivileged mode if you want to. Go right ahead. Actually, that would be an interesting adventure there to how to implement a little bit more of a secure approach for our operating system. We have it tough enough as it is. So I just chosen not to deal with that. If we were dealing with memory protection and virtual memory and all of that, then we would start to deal with user mode and protected mode.
So I guess I don't understand then what the point is. If we already know we're in supervisor mode.
We don't know that we're already in supervisor mode. The point is this code could be called from an interrupt, or it could be called from the process. So we may be in IRQ mode, we may be in supervisor mode. We know that we want to switch to supervisor mode, dang it. So this is what this is doing. It's switch to supervisor mode, dang it. Okay?
There are differences between supervisor mode and what they were used. A privileged mode?
Okay, so a privileged mode is a classification for modes of the processor. There are several modes of the processor which are classified as privileged modes. Supervisor is one of them. IRQ is another one. Okay? Other questions? Okay, so switch to supervisor mode, dang it. And now we have this next instruction. Load into R3, 0 off of SP. What is SP pointing to? Which SP is it? Supervisor mode. We haven't switched to the new process yet, but what we're doing is we're grabbing from the top of the supervisor mode stack. Well, okay, what's the last thing we pushed onto the stack? Right here, we stored R3, SP, pound -4, bang. So up there in this group of instructions that I've labeled 3, we pushed R3 onto the stack. That was we pushed the top of the stack onto the top of the stack. So are we just going to read this top of the stack off of the top of the stack when we're doing this load? Did we just push something on to read it back off down here in 6? It depends on if we started in IRQ mode or we started in supervisor mode. Okay? If we started in supervisor mode, these instructions at 5 convert us from supervisor mode to supervisor mode. The instruction in 6 loads into R3 the top of the SVC mode stack, which is a pointer to the top of the SVC mode stack. So what we're doing is we're loading into R3 the top of the stack. If we started in an IRQ, what we're doing over here is the IRQ mode stack pointer is pointing to some location, okay? And we're pushing stuff on, and so the IRQ mode stack pointer is incrementing or decrementing, going to more negative addresses as we push stuff onto it. There is still a value in the SVC mode stack pointer register. Whenever we're pushing inside IRQ mode, the SVC mode stack pointer register does not change values. So at one point, when we finish the ISRs, we're going to have the SVC mode stack pointer pointing at the same location as the IRQ mode stack pointer. Both those stacks are pointing at the same spot. When we get into here and we push stuff on, we're moving the IRQ mode stack pointer, but the SVC mode stack pointer is staying at the same spot. Okay? What this does is it reads off whatever the SVC mode stack pointer is pointing to. So when we're in an interrupt, what the SVC mode stack pointer is pointing to is important, and we need to keep track of that, and we'll get to that when we dissect the ISR file. But what 6 is doing is it's copying whatever's at the top of the SVC mode stack into R3. Okay? Then what we do is we say MSR, CPSR, C, R2. So what we're doing then is saying, okay, I know what my original mode was. I kept track of what the CPSR was in R2. I changed myself to supervisor mode. I'm going to change back to whatever I was. So if I was in supervisor mode when I started, I'm just switching to supervisor mode, calling it good. If I was in IRQ mode when I started, I'm switching back to IRQ mode. So now I say move R3 into SP. Which SP? Whatever mode that I was in when I started this code. Okay? So I read from the top of the SVC mode stack an address. And over here, I'm moving my current mode stack pointer to be whatever I read off of the top of the SVC mode stack pointer. Okay? So what that means is the top of the SVC stack has a pointer to some location that I'm going to use as stack. And I'm going to update my stack pointer with that. What that has the effect of doing is if this is a cooperative swap out, so if this was called not from an interrupt service routine, what I do is I push a pointer to the top of the stack onto the stack, and I read that pointer off of the stack, and I set my stack pointer equal to it. So what I've done is I've got my stack pointer pointing here. I've got R3 pointing there. And what I do is I switch my mode to supervisor mode, which does nothing. I read from the top of the stack, which is whatever R3 is already pointing to the top of the stack, so I read from the top of the stack into R3, which makes R3 point at whatever it was pointing to just before. It doesn't change its value. I change back to supervisor mode. Well, I'm still in supervisor mode. And then I move R3 into SP. Well, SP was still pointing at the top of the stack. So all this business is the hokey pokey, you know. You push a pointer to the top of the stack, onto the stack, you read it off, and you put it on, and you point your stack pointer at what it's already pointing to. So if this is a cooperative swap out, it doesn't change anything. It makes all the difference when we have a preemptive swap out, when we're calling this from an interrupt service routine, because the SVC mode stack pointer from an interrupt service routine is not pointing at the same location as the IRQ mode stack pointer, and so we read the original IRQ mode stack pointer off of the SVC mode stack where it's pointing to, and we restore that. So this is critical because it makes it so that our IRQ mode stack pointer points at what it was originally pointing to before we started the whole mess, before we got into the interrupt. So it points it at the original shared IRQ mode stack. Now, from 9 on, I start to restore the context of the process that I'm swapping in. So what do? I'm going to treat R1 as if it were a stack pointer. It's a pointer to the context of the process that I'm swapping in. What does that context look like? It looks just like the context that I swapped out. It's got a pointer to the top of the stack at the top, followed by CPSR, followed by all the registers. I'm going to add one slot to it, so I'm going to increment it by 4. Effectively, what I'm doing is I'm popping off the value that's stored at the top of that stack and discarding it. Why? I don't need it. On 10 here, I'm going to load into R2 whatever's at the top of the R1 stack, and I'm going to increment the top of the R1 stack. So if you remember, we have pointer to self, CPSR, all the registers. 9 pops off pointer to self. 10 is going to pop off the CPSR of the new process, and then the MSR here takes that CPSR value of the new process I'm swapping in and moves it into the CPSR register. Okay. Then I move R1 into SP, so that points the stack pointer register at the top of that R1 stack. This is where all the new processes registers are stored. And then I do the LDMFD, which unloads the context of that new process into the registers and causes me to return to wherever that new process was running. I told you it was messy. We're not done yet. Okay, so the next set of notes that I've got is basically just reiterating what I've already talked about. Okay, in order to really understand what this context switching is doing, you have to always be asking yourself, what mode am I in? What mode is the processor in? Why is it in that mode? What's the stack pointer register pointing to? Okay. So let's suppose we're doing a cooperative swap out and a cooperative swap in. Remember, we're calling CS from a C program. We're passing A, the address of a pointer location where we want to write the top of the stack that we're pushing everything onto. We pass that in R0. We pass in B, a copy of the top of the stack that holds the context of the process we're swapping in. So because we're doing a cooperative swap out, what that means is CS is getting called from the process, not from an interrupt. Okay? So what that means is the processor mode is whatever the mode of the processor is in when we start executing our process. And we're claiming that that's SVC mode. Now, one thing that's good for health and well-being is identify why we're in SVC mode. We never changed out of it, but how did we get in there in the first place? We don't boot to it. Red boot does not give us the processor in SVC mode. So some code that we have puts us in SVC mode. You ought to find that. Okay, so the current processor mode is supervisor mode. Then we go to the first step inside the context switch where we push all the registers and then we push the CPSR. That gives us a stack frame. Looks like the following. Okay? So there's stuff on the stack. Why is there stuff on the stack? Because when you execute a program, there gets to be stuff on the stack. You've got multiple stack frames. You're pushing your call, you save registers. Sometimes your caller save registers. You've got your return addresses pushed on the stack, any registers that you need to save, local variables, parameters you're passing, so forth. All that's stored on the stack. Then you decide, okay, for kicks and giggles, I'm going to call CS. You get into CS. As soon as CS starts, you've got this old stuff that's on the stack, and then you're going to push all your registers. So we push all the registers, and we push the CPSR. Now just remember, we're pushing R0 through R10, FP, SP, LR, and PC. This SP is whatever the stack pointer was pointing to when we started before we executed the STMFD instruction. So it's a pointer to the top of the stack as it was before we executed CS. So we push all the registers, and we push the CPSR. So that's 1 and 2. Now step number 3, we put SP minus 4 into R3. SP at the time that we're executing this, you remember that STMFD has a bang on the SP. So what that does is it pushes all the registers and it updates the stack pointer to point at the last thing you pushed. Okay? So we push all the registers and then we push the CPSR, so the stack pointer is currently pointing at the CPSR. The next thing we do is we say whatever the stack pointer's value is, we're going to subtract 4 from it. We're not going to put that into the SP, but we're just going to subtract 4 from it. and put that into R3. So what that does is it makes R3 point at the next slot up on the stack, the next slot of where we're going to push something, okay? Then we push R3, a copy of R3 onto the stack. So that causes the stack pointer to point here, and this then becomes a pointer to whatever R3 is pointing to, or a pointer to itself. So it looks like what we have down here. Okay? So we've got the old stack data, all the registers, the CPSR, and then we have here, we point the top of the stack to the top of the stack. So R3, SP, and the top of the stack all point at the same memory location. Number 4, we save the stack pointer. So what that does is it says, I'm going to point this memory location pointed to by R0 at whatever the stack pointer points to. So this is how I remember where the top of the stack is as I'm swapping this process out. This allows me to reference this slot that I'm saving it to later on when I want to swap this process back in. Step 5, we remember that R2 contains a copy of the CPSR. Why does it contain the copy of the CPSR? Because we read from the CPSR register into R2, we pushed R2 onto the stack. We haven't waxed R2, so R2 still contains that CPSR value. We OR it with 1 and put the result into R3, and we copy the C bits of R3 into CPSR. That is the control bits. That puts us in SVC mode. Okay? So now we say in 6, load from SP, 0 into R3. Because of the fact that this is a cooperative swap out, the mode of the processor is SVC mode. That means this mode change doesn't do anything. That means SP is pointing at the top of the stack we just pushed everything onto. So this is still the old process's stack. Okay? So what we're doing is we're saying, okay, SP is the same guy we just pushed stuff onto. Load from the top of that stack and put that into R3. We're not popping, we're just copying from the top of that stack. We don't have a bang here. If we had a bang here, it wouldn't do anything, but if you're doing a pop, you would say SP, pound 4, or you'd say SP bracket, 4, and that would post-increment the stack. Okay, so what this does is it says, move into R3 a copy of whatever's on the top of your current stack. Well, what's at the top of my current stack? Because this is a cooperative swap out, my mode change didn't do anything. The top of my stack looks like this guy. So you know R3 is pointing here, SP is pointing here, and I say load from the top of the stack, put it into R3. So that says whatever the stack pointer is pointing to, grab me this, put that into R3. So that makes R3, which was a pointer to here, it now makes R3 a pointer to here. Doesn't do anything. Follow that? Okay. This is the hokey pokey where you put your left foot in and take it back out again. It's necessary for when we're swapping in, when we're dealing with preemption. Okay? But just remember that load instruction, we're doing cooperative swap out, we aren't really doing anything with that load into R3. Okay? Step 7 restores the CPSR to whatever it was before. Step 8 copies R3 into SP. Why do we wait until after we restore the CPSR to copy R3 into SP? Which CPSR is this? We're restoring the CPSR to what it was before in the process that we're swapping in. How does that impact things? Okay, the trick here is every time you write to the CPSR, you could change the mode of the processor. And what that means is your SP ain't what you think it is anymore. Okay? So, if you swap the order of 7 and 8, if you wrote R3 into SP and then you restored the mode of the processor, well, what happens if the process that you're swapping in was swapped out preemptively? You've just switched to IRQ mode, and your SP isn't that process's stack pointer anymore. It's the IRQ mode stack pointer. And all this gets messed up. So what we have to do is we have to we have to set the mode of the processor correctly first before we write to the stack pointer, because what we're doing is we're pointing the stack pointer to the process's new stack, and we want that stack pointer to be the right stack pointer register. So that way we can unload it in the proper mode of the processor. So if we swap these two guys around, we could run the risk of updating the wrong stack pointer register. So every time you write to CPSR, you got to think this could change the mode of the processor. So be careful about that. So restore the CPSR to what it was before, then move R3 into SP. Why did we use R3? Because SP is banked, and we have multiple copies of it. R3 is not banked. So R3 is the same regardless of what mode we're in. So we have to land the top of the new process into a location where it's safe to, where we know that it's not going to get messed up by switching the mode of the processor. So we use it as like a little temporary location. So we move it over to here, possibly switch the mode of the processor, then update the right stack pointer to what we want it to be. So this is what we have after 8. We've got the old process like here. We've got the old data, the registers, the old CPSR, the stack pointer has been pointing to the top of the old stack. The top of the stack is a pointer to itself, and R3 is a pointer over here. Okay? We've got the new process over here, which is R1 pointing to the top of that. It looks like the old process. So we've got the new process's state, the new process's registers stored on the stack, the new process's CPSR, and then the pointer to self, and then the top of that stack is pointed to by R1. So step 9 pops the top of the new process's stack. So and it throws it away. So the pointer to self on the top of that stack, we just discard it. We know that it's there, we throw it away. So now R1 is pointing to the new process's CPSR. Okay? So we pop the CPSR value off of the R1 stack, and we put that into CPSR. So that potentially changes the mode of the processor. Okay? So that will set the mode of the processor to whatever the new process was in when it got swapped out. So if it was cooperatively swapped out, we now set the processor mode to SVC. If the process was preemptively swapped out, we set it to IRQ. Okay, step 11, we move R1 to SP. What this does is it points the stack pointer register of whatever the mode of the processor is in. When we execute this mode switch here on 10, we set that stack pointer to point at whatever R1 is pointing to. And what R1 is pointing to is the top of that process's stack where all the registers are stored. And then on 12, we pop all the registers and return to whatever the new process was doing before it got swapped out. Okay? That's context switch. That's a simple one. So, you have to remember, we want to be able to call ISR, we want to be able to call a context switch from either from an ISR or from a process. The other complicating factor of why we have to do all of this is we want to make sure that we handle the interrupts with the processor in IRQ mode. If we just gave in a little bit and decided we want to be able to handle interrupts in SVC mode, and we just toggled as soon as we got into ISR, into an ISR, if we just said, okay, well, I'm just going to switch to SVC mode and handle an interrupt while in SVC mode instead of IRQ mode, a lot of this code goes away. But, again, because of the fact that we like the safety of having the separation of the banked registers for the two modes, we want to be able to handle interrupts in IRQ mode, not in SVC mode. So we're going to eat the complexity. Okay. An invocation of an interrupt service routine could lead to a context switch. It doesn't have to lead to a context switch. When we get an interrupt, we have to make sure that the IRQ stack is set up correctly, and if we end up context switching, we have to make sure that before we swap this process out, that we restore the IRQ mode stack to whatever it was before we started handling an interrupt. Because if we don't do that, then we could end up in a situation to where state is saved to the IRQ mode stack, and we lose track of where that state is because that state belongs to a particular process. And we don't have any rhyme or reason to when a particular process gets swapped back in. So typically on a stack, you push stuff onto the stack, and then you pop stuff off of the stack in the order, in the reverse order from when you push stuff on. So by virtue of the fact that we don't have any predicted order in which we call processes and swap them in and swap them out, we can't allow state to reside on the IRQ stack in any particular order because we can't unwind it in the right order. So we have to make sure that we clear the IRQ stack before we swap a process back, before we swap a process out and swap a new process in. And that is what this ISRs file is. So if you remember your ISRs file, we had basically before, push all the registers, call the function that handles the IRQ, then come back and pop all the registers. Well, now we've got a whole bunch of stuff. We're switching to use an STMFD, where we've taken push all the registers code, squished it all down into one instruction, and added a whole bunch of other stuff. And this other stuff is what we need to do in order to make sure that context switching works, so that we restore the IRQ mode stack pointer correctly, and we save all the state to the SVC mode stack of the process that's getting interrupted. And I will pick it up there tomorrow. Remember that Thursday is really Friday, and Friday's fall break, so. You can sleep in on Friday.
Yeah, luckily.
Remember that the macro stuff is due on Thursday. Lab 5 is posted. Due in a week. But it's due tomorrow. The macro code is due tomorrow. The lab is due a week from Tuesday. A week from yesterday. This stuff is all Lab 6 material. We will be done lecturing on Monday. Good luck. That's okay.